RBMs can be used for fraud detection in text-based data. Banks and financial institutions analyze vast amounts of emails, transaction descriptions, and customer support logs to detect fraudulent behavior. RBMs can identify unusual language patterns, like phishing emails that use suspicious phrasing or financial transactions that don't match a user's typical spending behavior. At this point, it's clear that RBMs are more than just math. They're shaping the way machines understand human communication. But the real question is, what's next? Are RBMs continuing to evolve, or are newer models taking their place? That's what we're about to explore next, the future of RBM research and where this technology is heading. Let's dive in. All right, we've seen how RBMs power recommendations, image recognition, and text analysis, but the big question is, what's next? Are RBMs still evolving, or are they being overshadowed by newer deep learning techniques? Let's take a look at where RBMs are headed and whether they still have a future in AI. First, let's address the elephant in the room. RBMs are not as widely used as they once were. A decade ago, they were a hot topic in deep learning research, forming the backbone of deep belief networks, DBNs. But as newer models like autoencoders, transformers, and GANs emerged, RBMs started to take a backseat. Why? Because training RBMs is tricky. Contrastive divergence, while effective, is an approximation. It doesn't always find the best solutions. Meanwhile, autoencoders and VAEs train using backpropagation, which is more stable and scalable. But does that mean RBMs are dead? Not at all. Researchers are still exploring ways to improve RBM training algorithms, making them faster and more efficient. One promising direction is persistent contrastive divergence, PCD, an enhanced version of the original learning process that allows RBMs to handle more complex datasets without getting stuck in poor solutions. Another exciting area is hybrid models, combining RBMs with deep learning architectures. For example, some researchers are integrating RBMs with convolutional neural networks, CNNs, to improve feature extraction in images. Others are pairing them with reinforcement learning algorithms, allowing RBMs to assist in decision-making and game AI. One of the most promising applications of RBMs is in quantum computing. Traditional neural networks rely on massive amounts of computations, but quantum RBMs, QRBMs, could leverage quantum mechanics to speed up training and handle larger datasets more efficiently. Companies like Google and IBM are already researching quantum-enhanced AI, and RBMs are one of the models being tested in these futuristic systems. There's also renewed interest in RBMs for privacy-preserving machine learning. Since RBMs can learn representations without requiring labeled data, they are being explored for applications where data privacy is crucial, such as healthcare, finance, and cybersecurity. Unlike traditional deep learning models that require vast amounts of personal data, RBMs can operate in unsupervised settings, making them a potential tool for privacy-focused AI solutions. So, what's the final verdict? While RBMs aren't dominating deep learning like they once were, they still have a role to play, especially in niche applications like quantum AI, hybrid architectures, and privacy-preserving models. And who knows, with continued research, we might see a resurgence of RBMs in the AI landscape. But now that we've covered the past, present, and future of RBMs, let's wrap things up. What are the key takeaways from everything we've learned? Let's summarize it all in the final section, RBM Concepts in Review. Here we go. Oh boy, we've taken really a deep dive into restricted Boltzmann machines, from how they work to where they're headed in the future. So let's bring it all together and recap the key takeaways. RBMs are generative stochastic neural networks that learn to recognize patterns in data by capturing hidden relationships. Unlike traditional neural networks, RBMs operate with two layers, a visible layer that represents input data and a hidden layer that discovers deeper features. The key difference: RBMs don't just memorize data, They learn probability distributions, allowing them to reconstruct missing information and even generate new data points. Their training process is unique. Instead of using backpropagation, RBMs rely on contrastive divergence, an approximation-based method that updates weights based on how well the model can reconstruct its inputs. While powerful, this training method comes with challenges. RBMs can be sensitive to hyperparameters and require careful tuning. Despite their complexities, RBMs have been applied in real-world scenarios like recommendation systems, where they predict what users might like based on hidden patterns in their behavior. They're also used in image recognition, compressing visual data into meaningful features, and text analysis, where they help machines understand and categorize language. However, as deep learning has evolved, RBMs have faced competition. Models like autoencoders and transformers have largely taken over tasks that RBMs once dominated. That being said, RBMs still hold promise in areas like quantum computing, hybrid AI architectures, and privacy